This is a talk by Mark Hertzberg about aspects of superfluid and quantum dark matter.
All right, so first of all, thank you to the organizers for this nice opportunity to speak and this nice workshop. So in the first part of this talk, which may be the main part of the talk, I'm going to talk about superfluid dark matter. And this is based on work with Jacob Litterer and Neil Shah, who are graduate students here at Tufts. So first of all, as we all know, there has been tremendous success of cold dark matter on large scales, coming from CMB, large scale structure, Baryonic acoustic oscillations, Lyman alpha forest, galaxy clustering, and all together paints for a rather consistent kind of concordance model where the pieces of the puzzle, at least broadly, seem to fit together on these large scales. However, some authors have suggested that there are possible difficulties with cold dark matter on galactic scales. And in particular, I'll focus on the Baryonic Fischer relation, which relates the observed baryonic mass of a galaxy to its asymptotic rotation velocity v. And so here's the data from a bunch of galaxies, and you can see with relatively little scatter, they fit this simple scaling relation, namely mass proportional to velocity to the 4. On the other hand, at least in simplified treatments of cold dark matter, it's suggested that it predicts a slightly different relation, namely mass proportional to v cubed. So whether this discrepancy here is a real problem for cold dark matter remains an open question, but it has acted as some motivation to suggest that we might be missing something on the scale of galaxies. And in addressing this issue, some authors have taken a rather radical approach, which is they attempted to modify gravity on galactic scales, or so-called MOND. So if we, instead of Newton's law, that the acceleration is proportional to mass over radius squared, suppose instead, following Milgram, we say that the acceleration is proportional to the square root of this. If we then set the centripetal acceleration to v squared over r, then the factors of r cancel, which is good because that then predicts little scatter. And then we get the relation we want, namely mass proportional to v to the 4, the scaling desired to obtain the observed Baryonic Fischer relation. Okay, so perhaps we should go modifying gravity on the galactic scale. On the other hand, implementing this in a sensible theoretical framework has proven to be notoriously difficult. So for one thing, we have a theorem, which is that the unique causal Lorentz invariant theory of just massless spin 2 particles at large distances is general relativity. So from this point of view, the only way you could modify general relativity would be to add higher dimension operators, which would be irrelevant on large scales anyhow. So there are some things you can do. You have to break some aspect of this. For example, you might give up the Lorentz invariance or something like that. But a possibility that I'll focus on here is that one could add new degrees of freedom. And in particular, suppose one adds new scalars. And if those scalars are sufficiently light, let's say massless, they could mediate a new long-range interaction, albeit they would have to have peculiar dynamics in order to obtain this new funny scaling relation here. So is this possible? Well, to sort of set our bearings, let's begin with a kind of simplistic attempt in this direction. So suppose you add to the standard model a new scalar that I'll call phi, which may or may not also play the role of the dark matter. And its dynamics is governed by some function f, which is a function of x, where x is this Lorentz invariant kinetic term for phi. And the function f may also depend on phi as well. And suppose this function f has two different asymptotic regimes. So first of all, when x is small, which is relevant to low densities, that's relevant to large cosmological scales, let's say f is just x. So in other words, you have a canonical scalar that you can quantize in the usual way and so on. But on the other hand, as you go to large x, which would be relevant to higher densities, which would be more relevant to as we go to galaxies, which of course are much denser than cosmological densities. Suppose f enters a new scaling regime, namely x root x, or what I'll call a 3/2 scaling. Now, by the way, you can dream up functions that have these properties. So here's just a random function that has these two different asymptotic limits. And it's perhaps important to highlight that by going to large phi, where these effects are important, you can stay within the regime of validity of the effective field theory, even though this term may dominate over the first term. And that's because if the field value is big, that does not, however, mean that the particle energies are big. So you can stay within the regime of the EFT. Now, obtaining this new scaling relation here is useful because if you write down the corresponding classical equation of motion, and here I'm writing it down in the static limit, you get a modified Poisson equation where the right-hand side here comes from this term, where we're coupling phi to matter, for example, through the trace of the energy momentum tensor of the baryons. And if you solve this modified Poisson equation, you get what you want, which is that the acceleration between the baryons is proportional to the square root of mass over r squared. And that, as I said, is the scaling we desire in order to obtain the baryonic Tully-Fischer relation. Now, this simplistic approach has two basic problems. One is theoretical. So if you have essentially a Lagrangian that has this scaling x root x, it turns out that when you study high energy perturbations on top of this Mondian so-called solution, those perturbations are superluminal. And I'll come back to related details shortly. The second problem is phenomenological, which is that although the scalar, let's say, becomes canonical at large scales, so the function f relaxes to the canonical f equals x, that doesn't mean that this new force suddenly switches off. It just means it introduces a more regular force, namely 1 over r squared. So we can sketch that as follows. So let's say this is acceleration versus radius. This dotted curve here would be the standard Newtonian 1 over r squared force law. And this blue curve is the new force provided by this new scalar phi. So in this regime, it's introducing the desired new 1 over r Mondian force law. But then at large scales, it's just going to relax to some 1 over r squared. And that means you're modifying GR on the large scales, which can compromise the success of GR plus CDM on the large scales. So what we'd really like is some framework that has the best of both worlds. So on the one hand, you want a massive, say, scalar or some massive degree of freedom that can play the role of cold dark matter on large scales, but that on the other hand, there is some new light or massless degree of freedom that comes into play on galactic scales to implement the Mondian dynamics. And that can be done using spontaneous symmetry breaking. And this was done in this nice work by Baryonic and Curie from a few years ago. So essentially what they did was promote that scalar phi to a complex scalar that I'll call capital phi, whose dynamics is governed by some global U1 symmetry. And I'll write the Lorentz invariant kinetic term x as such. Now here's an example of some function. F is essentially the Lagrangian or minus the Lagrangian for this field. So there's a first term here, let's say, which is that of a canonical, now massive scalar phi. And so this term can be used to reproduce the success of cold dark matter on the large scales. On the other hand, there's some second term here, which has these peculiar scalings in it, okay, including x plus m squared phi squared all cubed. And this second term will be more relevant as you go to larger densities. And it turns out this allows for a phase transition to a superfluid state at you can choose parameters such that it kicks in at galactic densities. Now, by the way, just a reminder that if we're talking about superfluids, on the one hand, of course, they are very quantum from the particle point of view, but their standard dynamics is essentially classical from the field theory point of view. So in this part of the talk, I'll essentially just be talking about classical field theory, and towards the end of the talk, I'll say a few comments about really quantum behavior in a different context. In any case, if we decompose phi in terms of its modulus rho and phase theta, due to the spontaneous symmetry breaking in the superfluid, this theta acts as a massless Goldstone and can therefore act potentially as a long-range force mediator on the galactic scales. In more detail, having factorized out the rapidly varying e to the I mt, we're left with a slowly varying phase theta and modulus rho that describe this superfluid condensate. It's useful to write out x in terms of rho, and it turns out that at low energies, theta gets packaged into this function here that I'll call y as follows. At tree level, you can integrate out the relatively heavy modulus or Higgs mode rho, and then write down the low energy effective action just for the Goldstone theta. And it turns out to be this, where it goes like y root y, precisely the 3/2 scaling. So by coupling to baryons, this Goldstone can mediate a Mon-like force and reproduce the observed baryonic Tully-Fischer relation on galactic scales. On the other hand, as we move away from the superfluid and we leave the galaxy, we go back to the regular phase, which is just that of a massive scalar, which can reproduce the success of cold dark matter, and there is no remaining long-range force mediator, so we will not have any undesired fifth force on cosmological scales. So this all looks rather promising. Now, in this work, we wanted to put these ideas to some kind of theoretical consistency tests. So suppose you decompose this complex phi in terms of its real and imaginary components, and you look at perturbing around the superfluid by some perturbation epsilon, which I'm going to allow to be a high energy or relativistic perturbation on top of this condensate. You can write down the linear equation of motion for these high energy perturbations, where you just focus on the terms that involve two derivatives acting on epsilon because you're interested in high energies. The coefficients here depend on derivatives of f with respect to x, where again, in this example, f was this peculiar looking function here. So you have a pair of coupled high energy perturbations, coupled modes, and which you can readily diagonalize. It turns out that the perturbation in the Goldstone direction is regular. However, the relativistic perturbation in the Higgs direction is non-standard. So it obeys a kind of modified wave equation in terms of some kind of effective metric, which I'll call capital G mu nu, and it has this form. So if this effective metric governing the relativistic perturbations has some peculiar features, it may potentially compromise the causal behavior of the perturbations. And that's what we wanted to analyze in detail. So if we take this effective metric, one thing that it needs in order to have regular perturbations is that its eigenvalues are Lorentzian, so minus plus plus plus, in order to have regular wave propagation, which are also known as the conditions for hyperbolicity of the wave equation. And one can show that that requires first this coefficient here, f prime, needs to be positive. And another condition that needs to be obeyed is that some combination of these two terms, which turns out to be f prime plus 2x f double prime, also needs to be positive for hyperbolicity. If you have hyperbolicity and therefore regular wave behavior, you also need to check that the signal speed of perturbations is subluminal for a standard consistent theory, and that imposes this third inequality. So this connects to various older works, often done in the case of a single scalar. Here it's just generalized to the case of a complex scalar organized by U1 symmetry. So we then imposed or checked, I should say, these conditions on these superfluid dark matter models, finding that the first hyperbolicity condition is indeed always obeyed. However, the second hyperbolicity condition, B, turns out to be proportional to Y. And in the Mondian regime, it turns out that Y is definitively negative. So B is in fact negative. So the second hyperbolicity condition is in fact broken. Now, since the background primarily depends on time through the e to the imt phase factor of the superfluid, this breaking is in the temporal direction. So this is a kind of ghost-like breakdown. Albeit, this is not a Lorentz invariant ghost because the background spontaneously breaks Lorentz symmetry. Now, once you've broken hyperbolicity, you cannot meaningfully talk about signal speed propagation. On the other hand, if you move away from the Mondian regime to a kind of intermediate regime, sort of halfway between the cold dark matter on large scales and Mond on galactic scales, you can find intermediate regimes where you do indeed obey hyperbolicity, but then you can find parts of phase space where subluminality is broken and you get superluminality. Now, in this work, we went further and said, okay, let's consider the most general possible form for this class of theories. So you can write down a whole tower of operators as follows for this, essentially the Lagrangian F, with powers here, which have these various scalings. So there's an n upstairs and a 3n downstairs as I sum over n. And each term here, it turns out you need this scaling in order for this to recover precisely the 3/2 scaling in the low energy effective theory for the Mondian dynamics. All of your freedom then is essentially tied up in the choice of these dimensionless coefficients G sub n. If you choose G sub 0 to be positive, you will recover cold dark matter on large scales, and then the higher values of Gn dictate its galactic dynamics. So with all the freedom in the Gn, one might imagine that you could maybe somehow find a way to obey these conditions. But in this work, we could nevertheless prove a theorem, which is that there's a tight relationship between the following. So whenever you choose a set of Gn, which allow you to enter the Mondian regime, so any Gn's, you will get 3/2 scaling from here, but you will either get it with a repulsive force, which is no good, or you might get it with an attractive force, which is what you want for Mond. And precisely when you get an attractive force, which is what I called the coefficient alpha being positive in an earlier expression, that's the Mondian regime, you can prove that it's exactly linked, or at least it implies that B is always negative and you always break hyperbolicity. And it's always a kind of ghost-like breakdown. And as I said, you can also go to intermediate regimes where you find superluminality. So these are some what I consider to be kind of serious theoretical problems in this whole class of models. And I'll conclude these points at the end. Now to maybe shift gears a little bit for the remaining part of this talk, I wanted to talk about some more sort of quantum aspects possible of dark matter, okay? So in the first part of the presentation, we were talking about particularly superfluids, and we've heard a lot in this workshop, including earlier today, about things like boson stars, which are kind of some kind of condensate and so on, essentially studying systems that are scalars at very, very high occupancy. And so you might wonder, are there any aspects of light or say high occupancy dark matter that's not accurately captured by classical field theory, right? The superfluid was done in the classical field theory analysis so far in the talk. Just to give one example, for example, it turns out that if you study quantum radiation out of some kind of bound states, whether boson stars or oscillons, it turns out even at high occupancy, under some conditions, for appreciable self-couplings, sometimes the quantum radiation can actually beat the classical radiation even at high occupancy. And if that sounds counterintuitive to you, please, you can ask me more about that at the end. But in the remaining part of this talk, I want to talk about something sort of really quantum, okay, just for fun to see if it's possible. So it's important to remind ourselves that nonlinear dynamics, for example, can often change what you might have thought as a classical configuration can sometimes get organized into very quantum macroscopic superpositions, or what I might call a Schrödinger cat-like state. So as an example, if you take, say, a billiard table, and you put all the balls in a very classical state as an initial condition, and then you let them scatter off one another, because the system is chaotic, the tiny quantum uncertainties of each billiard ball actually grow. And for example, as pointed out in this paper, it takes about order 10 scatterings, and then the wave function spreads to be the size of the whole board. Okay. So it's not well described by a single classical trajectory. So you might get a kind of Schrödinger cat state of billiards in a frictionless system. Now, we usually don't care very much about this because this quantumness is essentially destroyed due to decoherence. There are all the air molecules passing through the room that scatter off the billiard table and ruin any residual, say, interference effects that might be lurking there. So we might ask the question about dark matter. So if you have some nonlinearities, and in some situations the nonlinearities can be appreciable, they could make quantum effects grow, or it might just be some peculiar initial state of the universe that we have dark matter, if you like, itself in a kind of macroscopic quantum superposition, a kind of dark matter Schrödinger cat, if you will. And this, for example, I'll often be interested in things like axions and so on, or typically light scalar dark matter that, as we know, can lead to macroscopic objects, over densities or bow stars and so on. Now, in this case, you can again ask, will the quantumness be destroyed due to decoherence? And in this case, it's less clear because dark matter has tiny, or perhaps no, non-gravitational interactions. So there's a chance that the dark matter quantum states could be the most robust against decoherence of anything in the universe. So could these dark matter Schrödinger cat states survive? Well, at the very least, the one thing that's going to try to destroy their quantumness is gravity. So here's the setup we had in mind. Suppose the dark matter is in some macroscopic superposition, states 1 and 2, that I'm just indicating here with this blue and red. And then there are all sorts of particles, say, moving through the galaxy, baryons, neutrinos, so on and so forth. And we'll call these probe particles. So if we're interested in the physics of the dark matter, how it evolves, we're often not going to be very interested in the probe particle. We're not going to track it directly. But what is the state? So initially, we might be in some kind of product state between these degrees of freedom. And then as this probe particle evolves, at the very least, it exhibits gravitational scattering off the dark matter. So from the blue region, it can say scatter to be in this position, so the green to the blue. But for the other part of the wave function, the red, the probe particle will get bent gravitationally a little differently and will end up in this other red position over here, roughly speaking. And so the final state of the system will be an entangled state, necessarily, between these degrees of freedom. If we don't care very much about these probe particles, naturally we would like to trace them out and construct a reduced density matrix, in this case just of the dark matter, and it has this sort of schematic form here, where the off-diagonal terms of the density matrix involve these overlaps between psi2 and psi1, where again that was the wave function associated with this final probe particle. And it's the size of these terms that's therefore controlling the size of the off-diagonal elements of the density matrix, which control true quantum effects, effects that we could never capture using classical field theory. So if this term goes to 0, it's sort of classical, however you cut it. But if these are large, there could be some residual quantumness in the system, albeit it may still be very difficult to measure. So we can compute this thing. Usually the gravitational scattering is rather small, so one can do this using some perturbative approach. So imagine this is a bit of dark matter in the galaxy and a baryon flies through it. The wave function for the baryon would be some unscattered, unperturbed piece plus a small perturbation. And you can compute the overlap in some expansion in powers of g Newton. And we stop at order g Newton squared is the first correction. So we can put in some parameters into this. So let's say each component, I'm just considering a superposition of two states. You could easily generalize this to n states, where each component has some characteristic mass, m1, m2, some characteristic inverse width or characteristic momentum mu1 and mu2. And it turns out that the perturbation from unity is something that I'm calling delta here, has this form, where these masses and scales appear here. These chi's here are some order 1 numbers typically that describe the shape of this configuration. And furthermore, this m is the mass of the probe particle. Here it's the non-relativistic analysis. And the d and the k, d is some width, and k is some momentum of the wave packet for this particle. But it turns out the d is not actually important when you do the following. So there's not just one particle, of course, that passes through the dark matter. We have zillions of particles constantly moving through the dark matter all the time. And each of them, as it passes through, scatters gravitationally a little bit and tries to reduce the off-diagonal elements of the density matrix. So you get some product that does that. So there's some kind of exponential fall off of those terms. And you can define a decoherence rate, which is proportional to the number density of the probe particles, their characteristic velocity v, and you have to do some integral over the impact parameter in the scattering calculation. And when you do that, it turns out the size of the wave packet drops out of the calculation, and you're just left with a formula that looks like this. Okay. So we can apply this formula to different situations. For example, if we consider the case of just light diffuse dark matter, say axions moving through the galaxy. So what's the relevance of them being axions? Well, axions, we know, are light, and so they have a de Broglie wavelength that can be large, for example, kilometers and beyond. And just from the virialized axions in the galaxy, they have mass density perturbations that are kind of order 1 from one de Broglie wavelength to the next. So there's some characteristic mass in that. And let's say that characteristic overdensity in mass for standard galactic axions has some order 1 quantum superposition. Then you can say use, for example, diffuse baryons in the calculation, and you get a decoherence rate that we computed carefully, but here's the rough scaling. It goes like the mass of the probe particle, the mass density of the baryons, the mass density squared of the dark matter, divided by some virial speed to the 9, and then the mass of the axions to the power of 8. So it has this very strong dependence on the axion mass. And so that leads to a decoherence time with this strong dependence. So if I plot that, it looks like the following. So here is the decoherence time for this dark matter quantum superposition, Schrodinger cat state in units of seconds, versus the dark matter mass, let's say light bosonic, or let's call it axion mass per particle, MA. The blue here is that in the galaxy. And this dotted line to guide your eye is just the current age of the universe. So for axion masses less than about 10 to the minus 6 electron volts, it decoheres in a time less than the present age of the universe. And so already becomes classical, however you cut it. Now, if you're interested more in detection, like in, say, ADMX ground-based detection, the dark matter axions have to move through the atmosphere, and that moves the blue down to this green curve here, and it moves down a lot because the decoherence rate is proportional to the density of baryons, which of course are much greater in the Earth's atmosphere. And so the decoherence time is much shorter. And then it turns out for axion masses less than about 10 to the minus 5 eV, it decoheres just as the axion goes from the edge of our galaxy, from the sort of upper parts of our atmosphere to our detector here on Earth. And so you're getting towards pretty much covering more standard axion masses from about 10 to the minus 5 eV and below will all be completely classical just from decoherence, gravitational decoherence. Okay. Let's see, 30 minutes?
About, yeah.
Okay, I'll be done shortly. Okay, so we can also apply this to, say, the case of boson stars, for example, that we heard about today. So if they were to, at some point, be organized into some quantum superposition, which is not implausible, given to form boson stars, we need appreciable dynamics in the first place, then the scattering is larger because they're so dense, they're so much more dense, and the corresponding decoherence rate turns out to be extremely fast. And so indeed, boson stars are once and for all completely classical. By the way, it's fun to do a kind of general relativistic extension of this idea. So for a couple of motivations. One is that our probe particles could be the much more numerous photons that are flying around and so on. But on the other hand, there's something qualitatively new that's allowed in GR, which is, suppose you have a macroscopic superposition purely of the phase of, say, of the axion as it oscillates up and down. Its spatial profiles are identical, but its phase is in a quantum superposition. This is something that you cannot see at all in Newtonian gravity, which was the calculation I just did. You have to turn on general relativity because this leads to oscillations in the metric. Okay, now, so we're talking about a full-blown quantum gravity calculation in some sense. And we can do that reliably. We don't have to be nervous about those words, of course, because general relativity is a well-behaved effective theory. We're certainly going to stay away from the Planck scale in this calculation. And it's a fun exercise to go through, which you can read about here if you're in the details here if you're interested. So you can start from the underlying QFT and derive a sort of relativistic Schrodinger equation in the sort of one particle subspace. So what I mean by that is I am going to assume that this one particle comes in and one particle goes out, albeit, of course, it's in a superposition. There are, in addition, there should be particle number changing processes, but those are suppressed by higher powers of G Newton. And so that leads you to a one particle Schrodinger equation, which has this form. There's a kind of Lorentz invariant operator here, and the capital phi and psi are just the components of the metric. So you can solve this thing perturbatively. I won't go through the details other than just to tell you that if you have just a superposition of phases and nothing else, then the decoherence rate has this form. So it's actually exponentially suppressed in the axion mass squared, the probe particle's energy squared. There's a mu, which is the characteristic inverse size of the dark matter, and k is the wave number of the probe particle. And putting this together, you get that it's roughly the exponential of -1 over v squared, va squared, the velocity of the axion, and the velocity of the probe particle squared. So if either of these is non-relativistic, the decoherence rate of the phase is exponentially tiny. And so that means that the phase is totally robust, at least against decoherence. So this may be relevant to direct detection. For example, if you take ADMX, they care about the phase because that leads to oscillations in their resonant cavity. And it's at least plausible that it's therefore in it itself is in a superposition of phases in the first place. Now, by the way, as a final comment, these velocities, could they ever be order 1? Well, they should be order 1 if you get near, say, a black hole horizon. So perhaps it's interesting that as you consider dark matter moving towards the horizon of a black hole, then every aspect of it becomes classical. And this, I don't know if it is important, but maybe it has some ramification for the information paradox. So just quickly to conclude. So in sort of part 1 of this talk, I just explained that superfluid dark matter is a novel way, perhaps the only known way, to obtain the successes of cold dark matter on large scales and the successes of MOND on galactic scales. And it does this in a unified framework. We studied a general class of models and proved that high energy perturbations always violate hyperbolicity. And it was ghost-like behavior in the Mondian regime. Intermediate regimes can exhibit forms of superliminality. And there are problems in related models too that you could read about here if you like. So this leads to an open question. So is there any other model free of these theoretical problems? Alternatively, can one rigorously show that we don't need to do this and that cold dark matter itself can reliably reproduce the Baryonic Fischer relation and other properties of galaxies? And finally, in part 2, I mentioned that macroscopic quantum states, or kind of Schrodinger cats if you like, of light scalar dark matter might exist and would potentially be robust against decoherence because of their weak interaction. We studied the decoherence of such states due to gravitational scattering from probe particles, and this is a kind of rigorous quantum gravity result. We found that superpositions of spatial profiles decohere rapidly for light, especially light axions, and boson stars decohere extremely rapidly. On the other hand, we found that superpositions of the phase of oscillation of the axion can live exponentially long, and it may launch detectors into superpositions. Non-gravitational interactions, however, if you're thinking about detection, can be considered in future work, was not done here. It's a very different kind of calculation. And finally, I mentioned that relativistic states that might be relevant near black holes decohere quickly, including the phase. All right, so thank you very much for your attention.
Thank you, Mark. Please, questions. I see Diego has a question. Diego?
Hi, thanks a lot. For the last point of the correlation of phase here, if this is detected in the lab, what did you learn from the microscopic model?
So it was a little bit hard. I think there's some static. Are you asking about this point here? How would this affect your laboratory?
Yeah, sorry, I'm in a bus now because I didn't know about this talk and I joined late. Sorry. I wonder which kind of models would generate phases that you could really detect on the lab. Which kind of correlation you would expect from some models.
So which models lead to a quantum superposition in the first place? Is this your question?
Yeah,
yes.
Yeah, it's a little bit hard, I think, to compute because you have to track the quantum state through the history of the universe, in principle. Okay, so nonlinear dynamics, certainly you enter this the moment your system has some kind of chaos, and then it just takes a few scatterings and it will interact. So ironically, for the lighter axions, their interaction rates are more important. So this is not the same thing as what others have spoken about as the relaxation rate, which is also important. But there's just an interaction rate that allows modes to move up and down. And for typical axion masses, that interaction rate is somewhat appreciable. Doesn't mean that it relaxes to equilibrium. But if you have appreciable interactions, then the wave function should spread and spread and spread. You may also have a model where some initial conditions put you in some quantum state from the beginning. I mean, that would depend on details of the early universe. But I think it's difficult to track the full evolution from the early universe to be sure that it ends up in a Schrodinger cat state. But what I would say is that the argument that it should be totally classical because the occupancy is big. The occupancy is big, maybe it's 10 to the 50, 10 to the whatever. But if you have some nonlinearities, the wave function is jumping exponentially, so it could catch up. So it's plausible, okay, but it's not proven at this point that it would be a quantum state.
Okay, Xavier.
Yep, Mark, thanks a lot for this very nice talk. I was wondering, so now when you talk about the coherence of, when you talked about the decoherence of the phase, you found that the result is exponentially suppressed. And this claims, or this shouts loud that perhaps the next correction is actually the leading contribution to this this rate. And so I was wondering, have you thought about what would be the next leading order correction to your result? And will it also be exponentially suppressed?
So you mean going higher order in powers of G Newton in this expansion? You mean like, yeah, okay, we stopped here at order g squared, and then there's some g cubed, for example.
For example, but all the other approximations you had to do.
From this point onwards, this is, I think, correct from this point onwards. Once you truncate at order g squared, you can reliably compute, because these rates, there is a well-defined perturbative expansion we go through, which is, well, it is just this expansion, but you can carry out and compute these terms here. So yeah, I think that this is reliable. It's related to the fact that these oscillations here, when the probe particle comes in, so if you had a static configuration like this and you go through, the big contribution to the scattering, or say cross-section, is, in the forwards direction. And so in fact, if you had a monopole, there's some divergence in the forward direction. That's the primary contribution to the scattering cross-section. But when you have something oscillating and there's no spatial superposition, then these oscillations provide a kick to the energy of this particle. So it's, if you like, from the point of view of this particle, it's no longer an elastic collision because it sees a kick provided by this source. And this kick jumps you away from the possibility of having any divergence in the forward direction in the scattering amplitude. And so it just totally suppresses the rate. So the rates are always e to the something, but usually you get like e to the something near zero because you can have a divergence in the forward direction, but now it's suppressed. But so I'm not sure we can ever beat this. There is a calculation, for example, that there is an analogous type of calculation to this that you can do in, say, one-dimensional quantum mechanics that exists in the literature, where they have a potential that oscillates like this, and they can solve the Schrodinger equation exactly, and it's also the same result. It's exponentially small. If you had a funny shaped axion, if the spatial profile had some jagged properties to it, you would have to be there's a subtlety there. But assuming the axion profile is kind of regular, sort of smooth profile, in other words, it does not have support itself at high momenta, then you should be exponentially suppressed.
And the fact that the exponent is proportional to the mass squared is related to what you said, right? I guess the kick that these particles get is proportional to the mass somehow.
That's right. Yeah, you're seeing the frequency. It's the frequency shift. Yep, where essentially energy shift is related to the axion mass.
Okay. Well, thank you very much.
You're welcome.
Any other questions? Andreas, I saw you had a question, but you withdrawn it, right? Okay. So with this, I see no more questions.